Thanks very much for the invitation. It's a great pleasure to speak here. And I think we're already at the end of today, so I imagine most of us are very tired, so I will talk about some simple stuff. So I'll start by something simple called simple curves, simple geodesic. But for talk about geodesic, I will just fix some hyperbolic surface. X will be a hyperbolic surface of genus G, greater or equal to 2 to have a hyperbolic metric. And of course, this surface is supposed to be a very nice surface, meaning compact, connected, oriented, everything you want. So, so what's a simple geodesic? We say a closed geodesic is simple if it has no self-intersection. Intersection. I'll give you some examples. This is my surface. Oops, oh, sorry. So this one, this curve, and all of these three curves will hyperbolic geodesics will be simple. Sure. But for example, clearly this one is not simple because it intersects itself at this point. But sometimes simple geodesics could be sort of complicated. For example, start to do something like this. And then go to the other side and re-close myself. And this is also a simple geodesic. But this is not simple. Okay, yeah, some examples. So what I'm interested in for those simple geodesics, you can always ask questions, for example, from 2 points of view. Topologically, the simplest question that you can ask is whether it's separating or not. Which means that if you cut your surface along this curve, will your surface be decomposed into several different connected components? And if it's not, then it's not separating, and if it is, then it's separating. And geometrically, you can ask about what is the length of it. And because you have a hyperbolic metric on your surface, which gives you a length of this geodesic, that will denote by the length of your curve gamma, say a curve gamma, with respect to your hyperbolic metric. This is the length of, yeah. So, yeah, you can, this is a simple curve. There's something slightly less simple, but still very simple. It's called multi-geodesics. A multi-geodesics or geodesic, I'm not sure. It's simply it's called a multiset of this important point of disjoint simple closed geodesics. So the multiset means basically that you can have multiplicity for the elements. For example, this set is, this thing as a multiset is not equal to A, B. So this element has multiplicity 2. And all these, of course, example, I will just retake this curves. The surface with these 3 curves, but now I can put all of them together. And they have multiplicities. For example, I can see that this one is my gamma 1, this one is my gamma 2, and this one is my gamma 3. And this element appears twice, and this is once, and this 6 times. So I can write like my multi-geodesic something like a formal sum of the 3 simple closed geodesics. Another way to understand it is this is just one single geodesic, but it traces out on its image several times. For example, it's 6 times, twice, and it's only once. So the idea is that you want to put simple objects together, but avoid all possible intersection. No self-intersection and no intersection between them. And in general, you can always write any multi-geodesic in this sort of formal sum as you can have M1 plus something, just mk gamma k. And all of them just curves like this, and this numbers the positive integers. And of course, you know that there are some conditions for k because you cannot have too many of them. This should be smaller than, I'll tell you directly, 3d minus 3, which corresponds to, in fact, the Pant's decomposition case, which means that when you cut your surface along all these curves, maybe I'll also give you an example here. A Pant's decomposition is something like this. Actually, this one is already a Pant's decomposition. And once you cut your surface along those curves, you get actually all the pieces. Boundary like this. Oh. Yeah, not very well drawing, but I think you know the idea. Great. But you cannot have more, so this is sort of the maximal case for multi-geodesic. Okay, so for multi-geodesics, you can also ask exactly the same question about topology and geometry. And in topological side, you can still ask whether it's separating. But it also has some even richer structure, which we can ask is the number of connected components. There are actually many other things, but they will just be as simple as possible. Number of connected components. For example, for this one and also this one is 3. You have 3 different connected components. And geometrically, of course, you still have the length of it, which we well defined. You can call it total length. Which will be defined by just linearly extend the length by the definition for a simple case. And this is total length. And actually having some richer structure called length vector, maybe I'll write it here since it's really important. You have some length vector. Which is in the place of just sum up everything, every length, just put them in a vector. Not really a vector, but yeah, it's a vector actually. Things like this. Okay, that's it. But normally this vector is huge, because normally your multi-geodesic will be something like this. So every component will be extremely long. But what you can do is try to get some normalized version of it. Normalized. Which is you just divide everything by the total length of it. And this vector will denote by L, but with a hat on it. To emphasize the fact that it's a unit vector. A unit vector, which means that this vector, it lives in the k-dimensional, in fact k-1 dimensional simplex, a standard simplex, which is by definition of x1 to xk, and all your coordinates are positive, such that the sum of all the coordinates is exactly 1. So it will be something which looks like this. For example, this guy is a simplex of dimension 2. This is 1, this is 1. And that's it. But actually I was cheating a little bit. Exactly, I think you remark. Because by putting them into a vector, you should know that which component comes first. Which means that your multi-curve should be labeled. But there is nothing natural in this story, because you don't know, I should give 1 to this guy, or this guy, or this guy. So there are several different solutions to handle these issues. But one of them that is also what we'll do is you have no idea how to order or label your multi-curve, but you know how to do for the real numbers. So you just take the decreasing order for the real numbers, for the vector. Which means that we'll take a flash here and take a flash here. It means that basically, if we I think continue with green. If I have a vector something like, for example, and it's not really a good idea to start with 1 here, 6, and 1. This is a vector on the simplex of dimension 3. If you take the decreasing order of it, it gives the biggest one comes first, and then clearly this vector doesn't depend on the order of this vector. So everything is well defined now. You don't need an order or labeling for this for your multi-geodesics. Okay, so this vector basically tells you what the length partition of the total length of a multi-geodesic. It tells you, for example, what is the biggest component, what's the percentage of the biggest components, like 60% or it's 10%, something like this. Basically, we want to understand the shape of multi-geodesic. It tells you the shape of it. Okay, so I think we're done with multi-geodesics. But what I really want to do is, the title suggests, it's some random stuff. So what is a random multi-geodesic? when we talk about random objects, you should know how to pick them. Multi-geodesics. And where to pick them. So where to pick them, you just take all of them. It's alpha. And alpha is a multi-geodesic on X. And then you want to be able to pick a randomly pick one, you need a probability measure on this side, actually. The formal way to define it. So if you believe, like me, that all multi-geodesics are born to be equal and no one is more special than the others, so you will want to put a uniform measure on this side. But it's actually impossible since sadly, this side is an infinite side. So it's sort of like you want to pick a random integer. But you know that you cannot do that. But there isn't a solution even for that question. It's like you don't know how to pick a random integer, but you can pick a random integer between 0 and a billion. Because since it's finite, so you just put a uniform measure on it, and then you pick one with respect to that measure. So here we'll do something similar, in fact. We'll just define some like complexity function, which is the length here, which means that we'll just pick those geodesics whose length are not very big, are bounded by a certain number. The number r can be huge. And luckily in this case, this side has a finite cardinality. And then you can we put a uniform probability measure on it. But of course, what you want to do at the end of the day will let this number go to infinity to get some true multi-geodesic, random multi-geodesic. It's like you can take a random number bounded by a certain number and then let that number goes to infinity. That's it. So this will give you some probability setting for this question, and then all the questions you can ask before, like about topology and about the geometry, you have a sort of like random version or quantum version of it, because then every question when you try to answer it, you will give you a probability. It's separating. It can be separating or not separating with certain probability. So, and in general, indeed, those questions are quite difficult. I can ask questions like, what's the probability of a random, say a random multi-geodesic is separating? What's the probability of it? And in general, this question is hard. It's not easy to answer. But things become much easier if you go to some asymptotic regime. And indeed, I'm also cheating a little bit, because when you are asking this question, your probability measure is in fact indexed by these two. You have to choose a large number r, and you choose a hyperbolic metric. So you should put something here. So this is a theorem. This is work by, maybe I should write down it here. Vincent Delecroix, Elise Goujard, Anton Zolich, antilithograph. And they answer this question in two regimes. You firstly you let R goes to infinity to get your real multi-geodesics. And finally, it turns out that once you let this number to infinity, the probability that you get doesn't depend on the hyperbolic metric. It depends only on the genus of it. And then you let the genus goes to infinity. And this probability will just go to separating 0. So it means that if you take a random multi-geodesic on a hyperbolic surface with huge genus, and you have no chance to pick a separating one, which means you cut it, you will cut the surface into many pieces. So it's sort of surprising in the sense that you have the impression that because for a general multi-geodesic, it will be something very long, it will be wandering around the surface. So when you cut it, you cut lots of things. But your surface will survive, actually. So what you get at the end of the day is that you have a hyperbolic surface with a huge genus and 2 huge boundaries. So for me, it's not very intuitive, but it is what happened. And secondly, you can also ask, so what about the number of components of such a multi-geodesics? It turns out that this number will be roughly log G divided by 2 when the genus goes to infinity. So you have lots of components. You have lots of components, but it's still non-separating. So it's sort of funny stuff. But this is not actually not really the topic of today. But we will really because those 2 questions are still topological. Topological question, and we will be interested actually for the geometrical question of this side. We're interested in the shape of the length partition actually of a random multi-geodesic on a large genus hyperbolic surface. So I think now I can state our main results. Maybe I just do a simple recap. So we'll look at this. This is, for the moment, is a function. It's a function. Maybe I can write it as you have this little flash. It goes from this site of multi-geodesic that I defined here, and it goes to. And here you have a small bug here because you don't know normally how many components you have. But you do know that the maximum case is 3G minus 3. So you can put something like 3G minus 3 minus 1. But actually we want to work on we want to put something together because but the problem is that when you change the genus, this one will change. But you have a canonical choice, which is you just embed everything in a simple active dimension, infinite dimension, which is actually the sequence of space of sequence, such that the sum converge and is equal to 1. And once you put all of them together, actually this function doesn't depend on R. The underlying map does not depend on R, but depend on this parameter. But since the measure depends on it, so it's better to write something like this. So our theorem goes as follows. Firstly, so now this is a random variable. It's a random, actually, it's a random vector sort of. It converges in distribution, whatever it means. When this parameter goes to infinity, to certain random variable that I will note by R. Actually, well, maybe I will come back to this random variable. It's totally explicit. It's actually a polynomial, but the expression sort of is slightly complicated. But just the most important thing for the moment, maybe not really surprisingly, but this thing doesn't depend on the metric of your surface. It only depends on the topology, which is G. But everything we'll look at is actually totally geometric. So it's sort of. But what's really funny is that now what you want to do is you want to let the genus goes to infinity. So when you do that, this will also converge in distribution to something called Poisson Dirichlet distribution. Of parameter a half. So whatever it is. But you have some direct corollary is that, now I'll take my notes. Yes. So you want to know the average value of your biggest or second biggest or third biggest component. So say the biggest, the longest will be, maybe I will just write nothing and write directly the result. Will be in average 65.8% of the total length. And the second one will be like something like 16%, and the third one will be something like 4.9% of it. The longest, second longest, third longest of your multi-geodesic. And if you sum them up, and of course you can continue, but if you sum them up, you already get like something like 97.8% of the whole total length. So it's something funny in the sense that you have some huge components. And on the one hand, you have lots of components. On the other hand, almost only very few of them are visible. You can see them. And if you take the first three of them, it's already everything that you see. Yeah. But I think now all of you may have the question is, so what is this guy? So what is a Poisson Dirichlet distribution? This is quite a funny distribution in the sense that it's quite universal, that you see it in many places, and it can be defined in various ways. I think the most simple manner to define it will be something called stick breaking process. Stick breaking process. It works as follows. You have a stick, something like this, of length 1, and you decide to cut it into many pieces, and you cut it randomly. So, but what you have is sort of a random number generator. You can have, once you press the button, you have a random number generated uniformly from 0 to 1. And that's only what you have. Basically, formally what you have is a sequence of, we say IID random variables, which means that all of them are independent and have the same distribution, which is the uniform distribution between 0 and 1. So it's just really a random number between 0 and 1. So what do? You just press your button, you get a random number, you get, say, like 0.3. So you say, okay, 0.3 is something like this. So I just cut my stake here. And this is my U1. And you see, okay, I have my first component of a random variable, which is x1. I define x1 in this way. Okay, then I just throw it off. You don't really do that, but you just forget it and then concentrate on the rightist stake. And then you take your second, you take again your random number generator, you press the button, you get a second number. Say it's 10%. So it basically tells you that how much, what is the percentage of stake you will cut on this working stake. So 10% somewhere here. So you cut your stake here. Get something like this. So what's the length of it? These small little pieces of this little piece. It will be something, it will be the length that survives after the first cut multiplied by the percentage of the second number. So what do you have? And you define it as your second x2. And you continue, for example, the third you will cut it somewhere here, and so on. So x3 will be 1 minus u1 times 1 minus u2 times u3. And then you continue. So finally, what you get is a sequence of random numbers. And almost surely that you will never stop. You'll continue this process, you have infinitely many pieces. But almost surely, if you sum up everything, it will give you 1. Which means that this random vector will be defined on the simplex of infinite dimension. And so, now what's the definition of I can write it down here. So it's a definition of the Poisson-Dirichlet distribution. If you take this one, you take this sequence of random variables, you reorder it in the decreasing order, and this one will follow the Poisson distribution, Poisson-Dirichlet distribution for parameter 1. This is not the Poincaré duality, by the way. Yeah. So, but this is. So now you have the question that maybe you have the question. So this is 1, but what we have is 1/2. So how can you get something like even more general, like Poisson-Dirichlet distribution of parameter data bigger than 0? So you should modify something here. It's a random number generator. And you will not take always a random uniform number, but something called a beta distribution of parameter 0 theta. And this is, I can write it maybe. So this is also a distribution, it's a nice distribution, it has a density function. And the density function is given by theta times 1 over x to the power theta minus 1. And it's supported between 1 and 0 and 1. And of course, you want some example and graphs. So if you take like data equal to 1, so this one is 1, this one is 0, so you just get a constant which is 1. So this corresponds to uniform distribution. I start here maybe. So this is 1 here. So this corresponds to data equal to 1. If you take data equal to 2, say, so you will start by somewhere higher, and it's linear, but it will always stop at 1. So you get something like this. So this is the density of it. You can also like take something maybe like data equal to 3, so we'll begin even higher. And finally, it's quadratic, but it's always finished at this point. This is data equal to 3. This one is data equal to 2. And of course, in our case, in the case of half, you will actually start by a half somewhere here, but when approach 1, it will explode. So basically it tells you that, for example, when the data is smaller than 2, you have it's more likely to pick a huge piece. It's a big piece. And if it's greater than 1, and so your measure will concentrate on this side. So you have the tendency to cut a small piece. So just sort of explain why you always say this big piece, because every time when you cut it, you have the tendency to cut a big piece. Something like this. Okay, this is the definition of the Poisson-Dirichlet distribution. And now we'll give you some examples. And you will see that why it's really a funny distribution. The first example we talk about will be the integer decomposition. We see maybe prime factorization. Now you really work with random integers. You take a random integer, say k, it's greater than 2. Say it's 60. You can decompose it as a product of prime numbers. In this case, it's 5 times 3 times 2 times 2, if I'm not mistaken. Yeah. So now you have you already see there are some structures, like there is a decomposition. You decompose something in a decreasing order, but it's product. So maybe but first of all, you just call this is the first, this is your biggest prime number with respect, in this decomposition of this number, which is k. And this one is your second biggest, third biggest, and so on. And you can look at this, you can put them in a vector. For any integer. But it's not on the simplest because the product is 1, but not the sum. But that's actually not complicated because you can just take the log. Once you take the log, it becomes something additive, and you normalize everything by the whole product, the product of everything, which is k. So now this guy, it lives on the simplex. So I can define a map which from any integer give you this decomposition. So this, maybe I can call the length partition normalized indexed by n, which goes from 2, 3 until n. And now since I'm stopped somewhere, so I can put a uniform measure on this side. And it goes to, I'm sorry about the math here. It goes to the simplex of certain dimension, but you will not bother with it. You just say it's infinite dimension. Okay. So there is a theorem. I will not write I'm not really sure about the guy who proved this. I'm sorry about it, but anyway, if you take this decreasing ordered length partition vector, it converges in distribution as n tends to infinity to the Poisson-Dirichlet of parameter 1. So this is the first example. And the second example will be the circle decomposition. for permutation. So I think everyone knows here that what a permutation is, but still, it's just it's an application from finite side, which is bijective. All of you know. Let us take an example. For example, 1, 2, 3, 4, 5, 6, 7, and 1 is mapped to 5, 2 is mapped to 4, 3 is mapped to, say, 1 and 2 here, and 5 is mapped to 3, and this is a fixed point, and this one is also a fixed point. So this is what we call a presentation of such a permutation. You just write down the whole map. But you can do that in a slightly more clever way, which is so-called this. You start with the smallest number. You write it down, and so it's sent to 5. Then you write down 5. So 5 is here. 5 is sent to 3, so you continue by 3, and 3 is sent to 1. So it's sent to this number. So you just close your bracket, and you restart with the smallest number in the rest of all of them, which is 2. So you take 2. 2 is mapped to 4. 4 is returned to 2, so you close it, and you restart by 6. 6 is a fixed point, and 7 is a fixed point. So this is called the circle decomposition of a permutation. So now I can you sort of imagine there is some very similar structure than here. You can define a similar random variable, which goes from the whole permutation group. But now you just pick a permutation randomly, which is uniform, which is a uniform measure on it. And it goes to simplex of dimension, infinite dimension, and you just associate every permutation to, say, I will say C1, which is actually the size of your biggest circle. In this case, it's 3. And the second one, etc. So in this case, it's just 3, 2, 1, 1. And of course, you will normalize everything by 1 over n to get something which lives in a simplex. So now you have a theorem which tells you that when you let this n goes to infinity, this converges to Poisson Dirichlet parameter 1. So you have some 2 or even 3 examples about the same distribution with different parameters, and this one is number theoretical, combinatorics, and geometric. So this is. But now you may have a question that the 2 examples that I give is they all have parameter 1. So how can you get some example with different parameters, say theta? It's not that complicated in the sense, for example, you can always work with permutation.
If you want to keep the void, you can pull the other one too.
Great idea. So I'm not sure that I know how to use this.
So that is the other one.
There is another one. Yeah. I see. Wow. Really high technology. So maybe put it here, something like this. It's more logical to be like this. Great. Okay, so how can we get something like with a parameter other than 1? So in the place of put a uniform measure on your symmetric group, you can also you want to essentially deform your probability measure. That's like what we do for the beta distribution, which is the deformation of your uniform probability measure. And by doing that, actually what you do is you define some weight for every permutation, which is, I will note by gamma is equal to, say, theta to the power of k and sigma. And this guy is just a number of circles of sigma. So in this case, it just will be 4. So it will be theta to the power of 4. And so you have a weight for every single permutation. And by definition, you defined your new family of measures. The probability that you pick this very permutation will be defined to be the weight of it divided by the sum of all possible, all the weights. And in this case, it turns out that this is just, if I'm not mistaken, it will start with theta plus 1, etc. So you say that if you take theta equal to 1, then you get a factorial, n factorial, which is actually the uniform probability. And this is something called evens measure for your symmetric group. And then you can look at the same question, but with a different measure. The theorem is, by the way, all of them are not our theorem. So in this case, this converges to Poisson Decomposition of parameter theta. So this, intuitively, the reason for this weight is, for example, if you take something which is greater than 1, and if you have many circles, then this number will be big. So it's more likely, so the weight of it will be huge. So you are likely to pick something which has many circles. And if the parameter, for example, is 1/2, then to keep this weight big, you will have to have very few circles. And once you have few circles, the length of the circle will be huge. So, yeah. So these are some examples about the Poisson Decomposition distribution. Maybe I can end by a small remark. Is that now you know that for a random multi-geodesic on a large genus hyperbolic surface, you know many things about them. It's first of all, it's almost surely it's non-separating, and the number of components will be roughly log j divided by 2, and the length distribution will be given by this Poisson Decomposition distribution of parameter 1 or of parameter 1/2, and also. So in many ways, their behavior, they behave really like the random permutation of the evens measure of parameter 1/2. And another evidence is that, for example, if you look at the average number of, you take a random permutation with respect to this evens measure of parameter 1/2. And you let the n goes to infinity. And now you can ask the question, how many circles will there have? Number of circles? Basically, there will be log n divided by 2. It's sort of like A rated, but it's log j divided by 2. So you already got the feeling that they are very similar objects, but the geometrical reason for this phenomenon is not very clear. Okay, so how many times do I still?
5 minutes.
Great, so I think maybe all those stuff are very quite funny, but so what's the another connection with maybe the conference? About the quantum. So maybe I will talk about the proof. but only the first ingredient, also the most important one. So when you are trying to deal with all those random multi-curves, since they are complicated in the sense of in topological sense, because they can have all possible number of components and the other topological structure. So what you can do is, how to say, maybe I will start by, you can ask, you can give them more conditions. For example, if I ask the same question, but I fix the topology of the multi-geodesic, so what will happen? Which means that in the place of consider this side, which is a multi-geodesic of I already raised it, which is alpha multi-geodesic x of length smaller than r. But I just put another parameter, which is gamma. Gamma is a given. Gamma is a multi-geodesic. And I will say that this alpha has the same topological type. Of gamma, which basically means that they are differ by diffeomorphism of the surface. An example will be, if this is my surface, then this curve will have the same topological type than this curve. But they are different. So once you fix them, you can ask the same question about, so now what happened with this guy? And you don't even have to put a decreasing order because you have the perfect control of the topological structure of your curve. And you don't even have to let it go to the simplex of dimension of infinite dimension because you know that it's exactly k number as a number of components. So this question is actually, and the whole project is initiated by Mariam Mirzakhani. And in her last paper, he asked this question and proved that if gamma is maximum, which means it's a Pans decomposition, then we know what happened. This guy will converge to the Dirichlet distribution of parameter 1, 1, many 1. And there are 3g minus 3 of them. So it's basically a distribution defined on the simplex of dimension 3g minus 4 of the density x1, x2 until 3g minus 3, x minus 3g minus 3. And of course, you have some normalized constant, but it's not very important. But it means that if you ask the probability that this random variable, you find this random variable in some open site, this is the open site of your simplex. So this probability you will go to the integral of this polynomial, of this monomial indeed, on this side. Of course, there are some normalized constants. So in the case of Pans decomposition, we know what happened. So you want to, and maybe now the natural question is, so what happened in general? This result is generalized by Araha and myself independently to an arbitrary multi-geodesic. And in this case, this will converge to some random variable. That's very similar to the one that I wrote in the theorem. But the point is, I think I will end the talk by some remark about this random variable. This random variable, it has a density. A density, because actually it's not that evident, because you start with some counting measures. You start with the simplex, and for every fixed r, you just get some points here. So for the measure, it's just the number of points in this side divided by the total number of points. But finally, since the number of points goes to infinity, what you get at the end of the day will be something continuous. And this density is actually a polynomial. And this polynomial, the funny thing is that the coefficient can be expressed by the intersection number of C classes on the linear manifold convectification of the moduli space of algebraic curves. And so it's sort of a funny connection between, because a priori we have no idea how this hyperbolic world will be connected with the purely algebraic intersection number. So I think it's maybe it's all what I want to say, and I will stop here. Thanks for your attention.
Thank you very much. Any questions, remarks?
Yeah. So how do these intersection numbers?
Yeah, I will give you some really rough idea. It's really the first order approximation. The proof of this part is by dynamic system. The approach. Basically, what you use is ergodicity of some called the Horror sphere defined by Milakani, and then you use stuff like the ergodicity of the earthquake flow, stuff like. But I can explain in a very simple way. You all know there is a problem. It's called Gauss problem. You have integer points in the plane, and you just draw a big circle, and you want to count how many points inside of this circle. When it's a radius, this is the radius r, goes to infinity, you want to know roughly there are how many points. Because our question is very similar actually. Because what you count is the number of geodesics with certain length constraint. But you know that actually another way to say the topological type is you act your mapping class group on this side, on this this gamma. So you just fix your surface and you let your mapping class group act on this gamma. You get many points, but you can also imagine that I will just fix this gamma and I will I will act the mapping class group on the surface. So the counting problem for the multi-geodesic is sort of a counting problem on the terminal space. So you can imagine, so this is your terminal space, and you have some points here, and what you want to count is the number of points inside of this big circle. But when you do this sort of problem, this is one approach. There is an approach is in the place of let this r goes to infinity, you can also say that I will keep it like just 1. But I will rescale the lattice. We will rescale the lattice, everything will be more and more dense, and finally you get the big measure. So it will roughly, the number of points divided by the rescaling constant will be like the area of your this disk which we apply. So you can imagine they're very similar idea for. So you do the same thing for this counting problem. So you rescore everything, but that's actually what you really do. But so the problem will be if you take the good rescaling, and then what you want to compute is the area of this disk, which is actually the area of part of your moduli space. And by the work of Mizakani, you know that the area of the volume of the White-Peterson volume of your moduli space with the certain boundary components is a polynomial. It's a polynomial, and the coefficient of the polynomial is given by the intersection numbers. And that's actually where there's one way to explain why those intersection numbers appear. But I'm not really satisfied or yeah. Sure.
Is there, so in the examples that you gave of other geodesic distributions, do any of those examples have geometric interpretations that make them look like the the original geometric?
You mean for the permutation and for the prime numbers?
Yeah.
Geometrical interpretation of it. I have no idea about it actually. It's but I think there is some. I think there does exist some universal model to describe this phenomenon. I think it's called logarithm combinatorics. That once your combinatoric structure satisfies certain conditions, and something very similar will happen. But maybe I will not say more about that but I don't know anything about the geometry of those examples.
Any other questions or comments? If not, we can thank the speaker again.
Thank you.